In this second part, I'm going to show you the complete definition of the discrete Fourier transform in 1D and how can we use that to analyze signals. So the discrete Fourier transform computes for every frequency u, and now I'm change here, I'm just using a variable u, starting with u equal to 0, and then for other higher frequencies. And for every one of those, it is computing the coefficient related to this frequency according to a sine and a cosine function that are implemented using a complex exponential. For an input array with n elements, the DFT 1D can be written as in this equation here. It is a little bit changed in terms of what we have seen, because I'm using x instead of t and u instead of omega. And also there's something important here, because now we are not in a Fourier series, we are using the actual discrete Fourier transform. So because we cannot go between minus infinity to infinity because we have a finite vector, we also have x between 0 and n minus 1, and a division by n in the term here of the exponential. So x's are all the array indices, and j is the imaginary unit, as we are going to see in below when we implement this function. If we want to do that, we can also use a normalization based on the square root of the number of the observation. This is just like after we compute everything, we divide by the square root of n, and then we have an amplitude of the numbers that are normalized. And f of u must be evaluated for u equal to 0, that's the first frequency, 1, 2, 3, 4, and up until n minus 1. So I'm going to consider that the function has number of frequencies that is the same of the number of values or the number of elements in the vector. I'm going to implement a DFT1D function. What we want to do is that we want to, for each frequency, so for each frequency n, so in a range between 0 and below n, I have to know n before that. So I'm going to take the shape of the function f that is given as argument to that function. So for each frequency between 0 and n minus 1, we are going to compute for each element of f. So for each x in range n, so also x 0 to n minus 1. So it's the same here, but for u. We can then compute the this function here, so this equation here. So inside this for loop here, this x loop, it's going to be this term f of x times e to the power of minus j 2 pi ux divided by n. So basically f of u, so f here in this case is equals to f of x times the exponential of, in order to say that this is a complex number, I just use a constant minus 1j. 1j in Python means that this is a complex number, so it's the complex imaginary unit, times 2 times pi, and then times ux, in which x is the point and u is the frequency, and everything in here is divided by the total n. So that's it. So in here, but remember that in this case here, I'm just computing for a single x. So what I want to do actually is to do that to multiple values. So for every x. So basically this is f of u. I have to create a vector capital F for every position u. And in order to do that, before going to compute, I'm going to create a vector of zeros with the same shape of the function that is being analyzed here, but the type of this value is complex. So I'm already defining that f, capital F here, is going to be a complex vector. So now I'm just summing it. It starts with 0, and then I'm computing this sum here. So sum for the first x and for the next x and so on. And that's it basically. This is the discrete Fourier transform for 1D. Let us just return the f, and I can include a normalization, which is dividing by the square root of n, as we see here. So pause the video if you didn't get it and try to understand what I just did here in those those two lines here. Should be the evaluation of one one value for u, or one frequency. Let us, I must have done something wrong here, so what is wrong in here? So 1 minus j times 2 pi times u times x. I don't need that, and then divided by n. Yeah, okay. Now it's okay. So it's divided by n. Let us define a signal based on a sum of sines and cosines with 200 observations. So I'm basically just composing a function here with sines and cosines as we did in the previous video. And the function looks like that. And I'm going to compute the DFT of this function. It is just computed, but the interesting thing is that we now have access to capital F, which is the DFT of the function f. So let us plot that. And because this is a complex number, if I try to plot the value f itself, it's going to give me a warning saying that this is a complex value, so it cannot show perfectly. So it is recommended to use the absolute value of the function. Okay. Now that we use the absolute value, what we have is the sum of the two components, the cosine and the sine, the real and the imaginary part. So we have all the frequencies that we want. However, as you can see here, we have 3 peaks in the beginning, and then we have another 3 peaks in the end. And if we see the frequencies that were used to compose this signal, those frequencies are 2 with coefficient 1, 8 with coefficient 0.6, and 16 with coefficient or amplitude 0.4. So you just have 2, 8, and 16. But what appears here are much higher frequencies. What it is happening here? Well, because of the property, the symmetric property of cosine and sine functions, the Fourier transform is also symmetric with respect to its central coefficient. So when we compute frequencies in between 0 and n minus 1, actually up to the half of the size, we do have the an unique frequency analysis, and then it repeats itself in a mirrored way. So it is kind of a mirror here. It's symmetric, and then it goes backwards up until the beginning. So in other words, what we can really analyze when we have a vector or any function in between that with n observations, what we are able to really analyze is in between up to a frequency of n over 2. So because of that, I'm going to show just a limited portion of the frequencies. Let us just create a frequency, a limited frequency, and then plot it again. And with R, I didn't need to do that. I could just use the okay. What I just did was, oh, okay. So I just taking the absolute value here. Yeah, that's it. So now we are seeing the actual value. If we have 200 values, we could analyze up to 100 frequencies, and this would be okay. But I'm showing you the first ones just to show that the actual peaks are matching the frequencies that we used to compose the function, which are 2, 8, and 16. So basically I have a peak here at 2, a higher peak, and then 8, and then 16. And it's decreasing because I use different amplitudes to compose the function. They were not using the same weight. They were weighted by 1.6 and 0.4, so increasingly lower. If I decrease here, for example, what I'm going to observe is a lower peak at that point. So the DFT has quadratic complexity, so it is big O of n squared, because for every for an input signal with n observations, we have to compute the function itself, so from 0 to n, to n minus 1, but we have to repeat that for between 0 and n minus 1 frequencies. So let us just make this function a little bit more efficient in Python by using array multiplication. What I'm going to do here, as you can see, this function here, it's similar to the previous one. However, instead of creating a for loop for x, what I'm going to do is I'm going to replace this for loop here by pre-computing x in a range between 0 and n, and then computing the multiplications regarding x all at once. So this part here that I just highlighted computes f, so the whole vector f with a complex exponential depending on x, which is now a vector. So it's basically doing that match procedure that we did in the previous video, but now for a complex exponential. And I'm summing everything and storing at f of u, a capital F of u. So you can see that this function runs in a much lower time in this case. So running time here for 200 values is something 0.005 seconds. If we measure the time of the previous one, so let me do that. So it's excluding the time to actually create the vectors. Okay. So right, so now this function here is using an additional loop. The running time was 0.35 seconds, so something around that, so 1/3 of a second. And with this new function here, it's the running time is much lower. So yeah, so it can run at least 100 times or around 100 times slower or so. So it is worth to check how to do that, how to make vector implementations or matrix multiplications using numpy in Python. Alright, so let us just apply this frequency analysis in images. Let us consider that each image is a one-dimensional array formed by a concatenation of its rows. So we did that in the previous video. We just fixed a row of an image and then and analyzed how the values varied along a single line. Because of the complexity of the DFT, this would be unfeasible for large images. Because if we have an image that is a one-dimensional array and an image is very high, that has a very high resolution, let us see here how it would behave. So for example, a 1 megapixel image would require a number of operations proportional to n squared. That means 1 megapixels is around 1 million pixels squared, which is 10 to the power of 12. If each operation requires 0.1 milliseconds, then the DFT would take in hours approximately that. So I just did a calculation here. So it would take for 1 megapixel image around 200 hours to process. Therefore, we are going to use here sub-images in the first analysis. However, there is a faster implementation of DFT known as the fast Fourier transform. We are going to see that later, but now let us just understand the concepts of the Fourier analysis. And the FFT, or the fast Fourier transform, is much more efficient in terms of computational complexity. I'm going to load two images, the two images that we already seen in the previous video, and then I'm going to extract sub-images with around 1000 elements, so 1024 elements. Let us just see here. So as you can see, I'm just taking parts of these images and then look into it as by fixing one value and then vary another. So I just as you can see here, this first one is probably a few lines, concatenated lines of this first image here. So it starts high and then decreases. So when I jump to the next row and start to in the beginning again, and it starts high again, and it is going in this direction. So it starts high, decreases, I get the next row, starts high, decreases, I get the next row, and so on. And for this image here, it's the same. So it increases, decreases, increases, decreases, increases, decreases, and so on. And it forms this pattern here. And let us take the DFT of both of them, this first one and the second one, and see how the frequencies are compared. let us just show part of the frequencies. I'm showing you a lot of frequencies here, but let me see if I can change, instead of doing two plots like that. Let us do, yeah, one of, sorry, so it's two, yeah, now there you go. And then we increase a little bit the size of the, yeah. Okay, so now that we know the concepts of the Fourier transform, we can see that the first image here has much more noise than the second one. The second one has variations, has oscillations, but the first one has much abrupt oscillations. And this is revealed by looking at the Fourier transform. Look how the first image has much more peaks along higher frequencies than the first one. The first one basically saturates around 100. If we just, let me just override that to 100 and show the first ones. So it basically starts very, very high here, so it has many frequencies up to maybe 60 or something, and then it drops to near zero. In this case, we have a much more influence of higher frequencies. Let's go back here, and much higher, so like 200 and so. So when we plot the coefficients using its magnitude, we are now trying to interpret real images, which may be more difficult. So real signals are much more difficult than artificial ones. However, there are important characteristics in such data, and then the image 2 has, as I just said, the image 2 does not have significant magnitude values before concentrated after 50 hertz. I was going to show not only the absolute value. Let me see if I can show the square root of that. Usually we do that. We square the number, the absolute value, to show what we know as the power spectrum. And then we can see here that the one function has more spreaded values of intensity values. The logarithm is also used a lot, so we can use the log to show, because the logarithm is going to to saturate the values. Okay, so now we probably want the whole spectrum here. So the first one here, which is the image with more noise, as you can see, it's much less behaved in terms of the frequencies. As we go here up to 250, it maintains the magnitude of the frequency components, but the other one also has some fluctuations. Okay, I'm going to leave it as it is. I just showed you the plot here, so it's basically the same. And then, so let me remove this logarithm here. Okay, and this is the logarithm of both functions. So note how the profile of this image shows higher coefficients along all frequencies, while the second one drops to zero, decay fast after 50 hertz. And then if we want to extend the 1D to the 2D version of the DFT, we have this formulation here, which is similar to the previous one, to the 1D DFT. So let me just go back a little bit. So this is the one. So in this case, we had f of x times complex exponential of minus j2 pi ux divided by n, sum everything. Now in 2D, we are going to have the two directions, x and y. So we have to sum along x and along y. And now also the complex exponential has two terms here inside, ux divided by n, which is related to the x direction, and vy divided by m, which is the variation along the second direction, which is y. So I'm just basically computing the summation of in both directions, x and y now. And the square root is now n times m, because it is the total number of pixels in the image. In order to implement that, we are going to use the same idea. Let me see if in here I just did that by using every value. I could use vectorized implementation. However, I'm just showing you how complex that can be. So I recommend you to take a look at this implementation. It is not that complex, so it just involves including a new term for the y direction and a new term for the frequency in the y direction, which is v, and that's it. And I'm going to compute that over an image with 32 by 32 pixels. As you can see here, it takes a while and approximately 7 seconds here for those two images. Oh yeah, for each one of them. And those are the plots for the magnitudes, the log of the magnitudes of the Fourier transforms for the first image and for the second image. I'm showing on the top the images, and on the bottom the Fourier transforms of those images. As you see here, so this image was like a zoom of the first one, and let me see if I can enforce, yeah, the values to be in between. Okay, so not normalize them. So when I don't normalize them, I cannot see anything, right? So I just have to rely on those. And then note that the first one here, the first value here on the corner, is related to the frequency 0 here, and frequency 0 here. And as we move along this space here, we're going to have frequencies at 0, let's say 0, 1, 0, 2, 1, 0, 1, 2, 1, 1, and so on and so forth. I'm going to show you in the next video how to interpret that a little bit better. But the idea here, so we can see that there is a peak in this corner, so it's very it's a much brighter value than the other ones. This is because when we compute the coordinate 0, 0, this coefficient is going to be actually the sum of all values in the input array. So if we use the definition of the Fourier transform and substitute here the the values of u and v with 0, because the 0 is a product, we have a product between 0 and all values here, and 0 and all values here. Everything goes to 0, and e to the power of 0 is actually 1. So the Fourier transform at 0, 0 is basically a sum of every value of the image divided by the square root of the size of the image. And this is why we plot Fourier coefficients using the logarithm function, because you want to see the also the influence of other coefficients other than the first one. Otherwise, we're just going to see a single peak. So I'm going to leave an exercise here. You can see at the notebook in that is at the repository, at the GitHub repository. But we are going to show, I'm going to show you in the next video also the theory behind this implementation and how to use that to actually process images. And the exercise is to perform the inverse transforms for the 1D and the 2D cases. Those are the equations for the inverse transform. As you can see here, we have f of x now that is equal to this this equation, and f of x and y, that's this equation that basically uses the Fourier transforms as input and inverts the signal of the complex exponential.